When technology had just begun turning digital, we were there, pushing the boundaries of system innovation, helping transform the most advanced and demanding technical industries, while enabling completely new ones that are now redefining the way we imagine the future. Unleash imagination. Turn great ideas into reality with Cadence.
Hello, everyone. My name is Nicholas Swart. I'm a CAD engineer at Analog Devices, and it's my pleasure to be presenting today. And I'm going to talk about some simulation results that we have obtained at Analog Devices using Cadence's 3D electromagnetic solver called Clarity. So let me begin. My presentation outline is as follows. So I'll give a brief introduction to Clarity. And then I've got two design examples I'd like to show, which I'll get into the details of that. And then that'll be followed by conclusions. All right. So what is Clarity? Clarity is, as I mentioned at the start, a 3D electromagnetic solver. And it's targeted specifically to 3D system analysis. This is a Cadence slide that Cadence kindly gave me. And it has very, very high capacity. And I will get into more of those details in my presentation, but it is specifically geared to run very large 3D electromagnetic problems to enable system level analysis where electromagnetic analysis is required. It's robust and so forth on compute farms. And again, I'll get into more of those details as I proceed. Although it's geared towards large problems, it can also easily run small problems, which I'll show. Okay. So what is the core technology in Clarity? There's some diagrams on the right there, which pictorially show a little bit about it, but let me explain it in words. So Clarity has a fine-grained parallelization algorithm that can take a large 3D EM computation and take all the steps in that electromagnetic computation. Those who are familiar with ED electromagnetic simulations will recognize some of these steps: adaptive meshing, frequency sweep, and so forth, and take those steps and distribute that computational work across a compute farm of machines, each machine itself having multiple cores. And the key thing to note with Clarity is not only does it distribute the computational work, but it distributes the memory required to do the computation. So it doesn't take a job, for example, and do one full frequency on one machine, another full frequency on another machine, with all the associated memory that would go for doing that full simulation on an individual machine. It does a much more fine-grained parallelization of both the computational work and the memory requirements, which enables very, very large jobs to be run in practical times. And I have examples which I will show in a little moment on that. It's also very efficient, so the overhead required to distribute or do the fine-grained parallelization is very small, based on what we've seen. And it's robust. So if you are solving a very large electromagnetic problem and you distribute it over, say, several hundred compute nodes in a compute farm, and one of those jobs fails, you don't want the entire simulation to fail. And Clarity, we have found, is quite robust, because when you're running large number of jobs on a farm, it's not that unusual sometimes for jobs to fail for whatever reason. The farm machine might fail, or the job might actually get killed by the farm management system and migrated to another machine. So you want Clarity, you want the solver to be robust in the face of that kind of thing. Okay. So on the value to Analog Devices that we see in this solution from Cadence is by a lot of our products in ADI now are system level products, multi-die, for example, on a laminate, large SoCs on laminates. And the more you can simulate of that system, the more you reduce risk and therefore increase the chance of first-time success. So that's one value add to ADI that we see. And particularly today when, for example, if a system is being built on a laminate, lead times for laminates through assembly houses now are very significant. The cost of failure is very, very large. So it's very important to have first-time success. You can solve large problems with Clarity without requiring very, very expensive server machines. So for example, once you cross the sort of roughly 1 terabyte RAM and say 128 CPUs, machines like that become very, very expensive to use or to purchase, excuse me. And in some cases, there may be problems that even a large, very large high performance server may not be able to simulate. Okay, so they are literally out of reach unless you have another computational method. And then system level optimization is possible. So if you can simulate, electromagnetically simulate a large system and you can do it in a reasonable amount of time, then you can contemplate things like doing system level optimization of signal chain from one end of the system through to the other, or whatever else you may be optimizing in that system. So that's another value that we see from the analog devices perspective. And then it goes without saying, perhaps, but it's worth mentioning that Clarity interfaces, excuse me, very well to both Allegro and the Virtuoso-based VRF tool, where some package layout can be done in Virtuoso. Okay, so very quick overview, and you'll excuse me, I just peek at my time here. Okay, so the first design example I'll show you is an ADI SIP product, a signal chain product. I've got a diagram on the left showing you the 3D view of this device, this product, and it's on a 6-layer laminate, which is about 12 millimeters by 6 millimeters in dimension, covered in molding compound, which I illustrated or shown on the top diagram there. 7 dies altogether. And the dies are all wire bonded, and 2 of them are piggybacked. Okay, and these are various analog dies that are used in this signal chain product. And then there's a total of 17 discrete components. The gray boxes you see there are the solder ends of those discrete components. So every pair of those represents one discrete component. And then a total of 84 package balls on this BGA. Okay, so this is not an overly complex design, but it's a design for which we have results from other simulators as well as some measurement results. And so we felt this, and it's a reasonably complicated design, even though it's not large, but we felt this was a good initial sort of test bench to run through Clarity to see what results we get. Okay. So in terms of simulation setup, we imported the design from Allegro SIP, and then we edited it using Clarity 3D Workbench. And this is a good point to just explain. There are 2 tools that form the Clarity tool suite. One is called Clarity 3D Layout, and one is called Clarity 3D Workbench. And the layout tool is targeted towards planar type structures, and it's very easy to set up ports for those typical type of planar structures. The 3D Workbench is a full 3D tool that allows you to add 3D geometries, do cutting of geometries, and so forth. Both tools use the same underlying Clarity engine. So depending on what you're doing, one tool is better than the other. You can move data from the layout tool, Clarity 3D Layout, into the 3D Workbench, for example, which is what we did here in the end. So we worked in Clarity 3D Workbench, and I'll tell you why in a moment. And then the part was covered with molding compound. We extracted a total of 38 nets on this particular product, which gave us 77 simulation ports in total. The Delta S mesh convergence was set to 0.01. So this is just the tolerance convergence on the mesh refinement step in the electromagnetic simulation, and that's fairly standard value to use. 0.02 is perhaps a bit more common. 0.01 is a little tighter, but not out of the realm of what's normally done. And we simulated from DC to 5 gigahertz. And the bounding box size was 10 millimeters plus or minus in every direction. An absorbing boundary condition, and that's the version of clarity we were using. All right. So how to just to a few points on how the simulation ports were set up for this this SIP product. So in Clarity 3D Workbench, we created reference planes on each of these die. So if you look at this top die here, you can see the dark purplish plane that was drawn in Clarity 3D Workbench. And then that plane was physically connected to the ground wires or the ground bond wires and pads for this IC. And then if you look in the top right, there's a zoom there, you can see a pad in the top of that yellow oval and a port between that pad and this ground plane. So that ground plane was used as the reference point for all the pads on that die, all the signal pads. Okay, so this is a fairly standard way to set up port references if you're doing a simulation like this. And basically, the assumption is that the die power ground network is fairly close to ideal, and you can reference these ports without too much error to an ideal ground that you draw on the die. Okay, so this was very, very easy to do in Clarity 3D Workbench. Very, very quick process to draw in this die ideal ground. And then similarly on the die below, you can see another ground there. It's not highlighted in purple, but you can see it there, and it connects to the ground pads on that die as well. And that was used for the references for the ports on that lower die. Okay, so all of this is very easy to set up in Clarity 3D Workbench. So that's the die side. And then on the package side, the package was put on a 2-layer PCB, just a generic PCB board. And then the power and ground network was physically connected to the bottom layer in that PC board. And then the top layer in the PC board is where the ports were connected, the signal ports, and their reference was that ideal PCB ground. So again, this is not, well, I should say, it's a very common way to set up simulations like this, and Clarity makes it very, very easy to do this. Depending on what you're doing, you may want different types of port configurations, but for common port configurations, it's very quick to do this in Clarity. Okay, so that's the simulation setup. So let's look at the results. Oh, I forgot one more thing on simulation setup. So the discrete components, the SMDs in this, we wanted to bring ports out for those. In Clarity, you can put models into Clarity for things like discrete components or for any component in the system. And then Clarity will incorporate those models into the final S parameter analysis. But in this case, we decided to create discrete ports for each of these, a pair of ports for each of these surface mount devices. And in this case, the ports, these two are the solder blocks for the SMD, and they're sitting on laminate layer 1, of course. And we just created ports from L1 to a system ground that was sitting underneath on L2. Okay, so for each one of those components, we created a pair of ports. Okay, all right, so that now is the simulation setup complete. And let's have a look at the results. So we ran this simulation in Clarity, and then we compared it to another commercial tool that we use in analog devices that we have used for a long time and we trust. And we got excellent comparison between the S parameters between Clarity and this other tool. I will talk about what I mean when I say simplified design in a moment. Don't worry too much about that. The two other tools here are the same tool. And as you can see, there's excellent agreement. And I have here on the slide, no tweaking employed. And what I mean by that is we didn't, often when you're doing a comparison between tools, You get good agreement once you start adjusting the dials on the one tool and adjusting the dials on the other tool. And when you get everything all lined up perfectly, then you get good agreement. That wasn't the case here. Right out of the box, Clarity gave us excellent agreement with this other tool that we trust. And in fact, we were so surprised by the agreement that we went and double checked our results just to make sure we hadn't made a mistake, which we haven't. And I'll show you another slide here of results. Again, just some more S parameters. And you can see that, again, the agreement is really excellent. So this was very, how would I say, just struggling to find the word, but this was comforting, okay, to see such good agreement right out of the box without a lot of tweaking having to be done, either with the other tool or with Clarity. Okay, and I'm showing you a very small subset of the accuracy and analysis we've done in comparison with other tools. And we in every case, we've seen good agreement like this. Okay. So this table summarizes the simulation results, the performance results. Okay. Now, design one, this is the design we're looking at. I have here design one simplified in this section of the table called other tool, which is the other tool. And design one simplified was just that same design where the geometry was slightly simplified to try and improve the simulation time when using that other tool, because we saw very, very slow simulation time when we used the design as it was. Okay, and we'll look at those numbers in a moment. Frequency range was 0 to 5 gigahertz, uniformly for all the sims, including for Clarity. Same mesh delta error, no memory limit set. And then if we look specifically at the results for the other tool, we were running on a large 1 terabyte machine, dedicated machine with 2 threads per 80 cores, so 160 effective CPUs. And that design took about 27 hours to simulate with the other tool, and used between 389 and 470 gigabytes of RAM. When we simplified the design, we were able to get the runtime down to about 9.5 hours and somewhat less memory usage, 274 gigabytes to 329 gigabytes. Now, turning to Clarity, excuse me, in the case of Clarity, we ran Clarity on the farm, on our compute farm. We have a very large compute farm at ADI. And when you run a job on a compute farm with Clarity, it makes its resource requests in blocks of 4 CPUs and 32 gigabytes. I'll probably repeat that a few times, but it's just because it's kind of burned in my brain. But 4 CPUs, 32 gigabyte chunks, that's a single resource request. So we made 20 resource, we allowed Clarity to make 20 resource requests. So that's a total of 80 CPUs, okay? And so that's half the number of CPUs on the dedicated machine with this other tool. And you can see here, Clarity ran in just 1 hour, 25 minutes, okay? And for any one of those 4 CPU, 32 gigabyte resource requests, Clarity used no more than 36 gigabytes. I'll talk a little bit more about the memory usage of Clarity in a moment, okay? So you can see here, just on the simple example, Clarity is substantially faster. And if I just step back to these one-page results, you can see there was excellent agreement with the other tool. So there wasn't, as far as we can see, any accuracy sacrifice that Clarity was making in order to achieve these excellent run times compared to the other tool. Okay, so that's the first simulation. Just some other metrics to look at here. So this is the runtime versus number of CPUs. So we tried different CPU counts and then observed runtime for that same simulation I just showed you with the delta S convergence of 0.01. And you can see here that about 60 CPUs, it appears that Clarity is bottoming out for this specific design. Now, I do want to stress that our compute farm at Analog is always very, very busy. And we don't know for sure if Clarity is sometimes waiting for resources. We haven't monitored that during the runs. But it's entirely likely that it might have been waiting, and perhaps, you know, the bottom of this runtime curve might have been 80 CPUs, but roughly it looks like at approximately 60 CPUs. You're not getting much more benefit beyond that for this somewhat small problem, which had 7.7 million unknowns. Just to see how this worked, if we, you know, sort of artificially made the problem bigger, if you will, we set the delta S convergence to an order of magnitude smaller, and then ran the same experiment. And in this case, the number of unknowns changed slightly in the simulation, depending on how many CPUs were being used. But again, you can see that clarity starts to level out at about 60 CPUs for this problem, okay? And not much performance improvement is seen beyond that. And again, I stress for this problem, okay? There are other problems where, you know, you may continue to see improvement in runtime well beyond 60 CPUs, okay? And then the data on the right here is just kind of one of many ways to sort of look at the stability of clarity when you push the mesh refinement very, very far. So again, we went from 0.01 to 0.001. So this caused clarity to go from about 7.7 million unknowns to about 25 million unknowns. And you can see that the S parameter data is still, you know, is very close. Obviously, the clarity had converged at 0.01. You can just see that from these results. But nonetheless, it just shows how stable the tool is when you push the mesh engine very, very far. And that's another encouraging result. Okay. Okay, so let's go to design number 2. And here we're looking at a much more challenging problem for clarity. So this is a laminate for one of our high performance transceiver SoCs. Okay, it's a multi-layer laminate. It has the BGA has over 3,000 balls. And this is one of the most complicated laminates that ADI has ever designed. And we decided to see, and it's almost 3 millimeters by 3 centimeters, excuse me, by 3 centimeters in size. And we decided to see whether we could simulate this entire laminate in clarity. And this is not something we would normally even contemplate in analog with the electromagnetic simulators we have. But we wanted to see whether clarity could do this. Okay, so just briefly again on the simulation setup. So for the ports on the die side, we put in an ideal ground plane and then put what are called coaxial ports, where the ground plane gets cut open and then the signal nets, the port for the signal nets in that location, or the signal bumps, let me say, go from the bump to the perimeter of that cutout on the ideal ground plane. And then power and ground were physically connected to that ground plane. So again, this is a fairly simple, fairly typical way of setting up ports for this kind of simulation. And in this case, we were using Clarity 3D layout. And this is a very, very, very quick process in Clarity 3D layout. So the signal nets were correctly annotated versus the ground nets coming out of Allegro. And so within literally about 2 minutes, we had all these ports defined on the die side for the simulation. Okay, so that's how the die side ports were done. And then on the package ball side, we use a similar approach to what we used in that other simulation I showed you, a 2-layer PCB with the power and ground nets physically connected to that bottom PCB layer, and then ports taken from the the package balls. I always get the balls and bumps mixed up. Package balls down to that ideal second PCB layer. And again, this is also very, very quick to set up in Clarity 3D layout. Once you know how to do it, it's a minute or 2 at most, and you can have this set up. So maybe 5 minutes from the time this design was brought in from Allegro to the point where we were able to start simulating. Subject to getting the laminate cross section all correct and so forth, but once that's done, it's very quick. Okay, is there anything else I want to say about this? I do want to stress that in this simulation we included the entire laminate. So none of the power nets were eliminated. Basically, everything that's a conductor in this laminate was included in the clarity simulation. Okay, so we approached this simulation in two ways because we were trying to understand how Clarity would handle a problem like this on a farm compared to a single dedicated machine. So the first simulation we did of this design was on a 3 terabyte machine, 64 by 2, 64 physical by 2 threads, 128 effective CPUs. And Clarity had this machine all to itself. So there were no other jobs running on it, okay? And the simulation setup, so we ended up with 126 signal nets in this particular simulation, 252 simulation ports. All the other nets were power and ground that were connected to those ideal planes, as I explained. We set a target convergence of 0.01, and we simulated from effectively DC. You can go to DC in Clarity, and from everything we've seen, it works very well at DC, but we did 1e to the 8 here to 20 gigahertz. So much higher frequency than what we saw before. There's the bounding box size, and we used an absorbing boundary condition. And we said to Clarity, you can use the full 128 CPUs on this box, okay? And we allocated a gigabyte. Turned out that was a terabyte, excuse me. Turns out that was, more than sufficient for what Clarity needed. But that was the Clarity, the memory allocation, and that's the version of Clarity. Okay, so first of all, let's just look at some simulation results. And these aren't comparison against another tool, because we don't have that laminate simply cannot be simulated with the other tools we have now. Okay, so that's the main reason why I don't have the comparison with other tools. That's why we used the smaller example earlier. But these are matched signal paths. They're not perfectly physically matched, but they're very closely matched. And so you would expect for each pair of these S parameters that they would sit on top of each other, and indeed they do. So, it's one way to get at least some idea of how the tool is performing. So, and these also look correct based on what these signal paths are. Okay, so this was an expected result and a correct result based on our understanding of these signal paths and other more dedicated simulations that we've done of those signal paths. Okay, all right. So let's look at the memory and runtime. So first of all, runtime. Remember now, this is a dedicated machine, 1 terabyte. It's a big workhorse. The initial mesh step took 2 hours, 47 minutes. Then the adaptive meshing took 3 hours. Then the frequency sweep took a little over 9 hours for a total of 15 hours. So even if I was to stop here, this is an impressive result, okay, for a problem of this size. So in 15 hours, Clarity solved this, and without failure, okay? But let's look at the memory. So we monitored the memory usage over time. So I've got this chart on the left here, and I'll just dig into this a little bit. So this is memory usage as over time as the simulation proceeds, and the initial meshing step, used about 50 gigabytes of RAM on this machine. The mesh refinement went up to almost 900 gigabytes of RAM, the 7 mesh refinement steps. And then the adaptive frequency sweep, used about 500 gigabytes. Okay, so this is a nice snapshot of Clarity's memory usage. So peak memory usage was at about 865 gigabytes. Now we told Clarity to limit itself to 1 terabyte, because at that particular time, the machine only had 1 terabyte in it. About a week later, it had 3 terabytes, but it had 1 terabyte. So Clarity behaved itself well here, but you can see that it was approaching that 1 terabyte limit to simulate this job, okay? In adaptive, in the mesh refinement step. And the final mesh size, so once Clarity had got to the final mesh refinement with a 0.01 accuracy, there were 13.5 million elements, 65 million unknowns, and the final delta S was just below 0.01. So because it always steps a bit beyond that. So 15 hours for 65 million unknowns is a very, very competitive result. Okay. However, and I think there's the Clarity version. Now remember, this is on a single dedicated machine. What we want to see now, of course, is how does Clarity do with this same simulation on Compute Farm? Okay, and this initial mesh step in the newer versions of Clarity is parallelized, and I have one data point on that to show you in a little bit, but that drastically reduces this initial mesh step as well. Okay, so 2 more simulations now, and this time on ADI's Compute Farm, which has a large number of machines that vary in CPU count, vary in memory size, vary in usage. As I said, the farm is often very busy. So it's a kind of, it's a diverse collection of machines on the Compute Farm. And the same simulation setup as before, 126 signal nets, 252 simulation ports, and so on. I won't go through all the numbers, but we replicated this exact simulation on the farm. And then we did 2 simulations. One was 256 CPUs, again in these 4 CPU 32 gigabyte resource requests, so 64 total resource requests. And then I'm sure you want to know the answer to 128 because that's what we had on that dedicated machine, and I will show you those results in a moment. But we also wanted to see what could be done if we went up to 256 CPUs on the farm. Okay. All right. So let's look at the results. So simulation 2A, that's the one using 256 CPUs. Initial mesh 3 hours, adaptive 4. Frequency sweep was about 8 hours and 40 minutes. So total time 15 hours, 45 minutes. And I'm going to jump back here. You'll see 65.3 million unknowns. You'll see here, if I can get my screen to go back, I apologize. Here we go. So 65 million.3 unknowns. So it despite the fact it was running on the farm and 9.4765, I want to just point this out. You'll see here 9.7465. So even though Clarity took this job and distributed it over the farm, it essentially replicated its results exactly, which is all in of itself very, very useful. If you're rerunning a simulation, designers tend not to want to get different simulation results, even if they're a little bit different. So if you rerun the next day and you use 128 CPUs, you get the same result, which is very good. Okay. And then let's look at the memory usage. This is where things get really interesting. Well, first of all, before I say that, the 15 hours 45 is very competitive to the time that we had on the dedicated machine. Now, granted, that had 128 CPUs. This is 256 CPUs, but nonetheless, and I say here noisy data because the farm was very busy. Okay, this is a very, very good time. And then the memory usage below here. So what we did was, for each one of those 4 CPU 32 gigabyte resource requests, we monitored the memory, the maximum memory usage that Clarity used for those. And as you can see here, both for the frequency sweep and the adaptive sweep, the memory usage stayed below 30 gigabytes for all of those except for 2. And one of them went to about 35, and then one went to 50. And to be honest, the one that went to 50, I'm not convinced that this isn't actually a data gathering mistake. So maybe we put a question mark over that. But the key point here is that Clarity is very well behaved with memory usage. Okay, so when you give it a 4 CPU 32 gigabyte request, it honors that. And then even perhaps more importantly than that, you can see what an amazing job Clarity does of uniformly distributing the memory usage across the farm for this problem. So it's taken a problem that we know on a single dedicated machine needed something on the order of 850 gigabytes to a terabyte of RAM. And it's broken it into these tiny problems and distributed them very uniformly over the compute farm and solved the problem that way. So this is very powerful from the point of view that you can access a lot of lower power, less expensive machines and solve a problem of immense size. Okay. All right. So now the question everyone I'm sure is wondering is, how did we do on 128 CPUs? Because that's what we had on the dedicated machine. So here you can see initial mesh 4 hours, then 3 hours 51 for the adaptive, 950 for the frequency sweep. So 17 hours and 40 minutes. And again, I have to just stress, this is noisy data. When this simulation was run, the farm might have been busier than it was when the simulation 2A was run. It's not certain, but nonetheless, 128 CPUs, same number of unknowns, 17 hours and 40 minutes versus 15 hours. So just 2 hours and 40 minutes less than a very expensive, very high performance single machine. And Clarity was able to take this job and spread it out over the farm and solve it. Okay, so that's not a huge time penalty. Even if we discount the fact that the farm might be busy, that's not a huge time penalty for such fine-grained parallelization of the problem. And again, here's the memory usage, and you can see again, Clarity is extremely well behaved and also does an excellent job of distributing the memory resource requirements uniformly over the farm. Okay, all right. So now I was talking about this mesh step being parallelized. So the initial mesh is when Clarity makes its first mesh for the system that it's simulating. And Clarity has a new mesh engine called xMesh, which parallelizes this step as well. And in earlier versions of Clarity, you couldn't parallelize this initial mesh. Everything else was parallelized. But now this is parallelized. And so using the 2022, a new release of the 2022 version, this initial mesh took only 52 minutes, okay, for 128 CPUs. So that's very substantial. So that's another 3 hours off the simulation time. So that brings this below 15 hours. Now, of course, if you use the xMesh on the single machine, that time would come down as well. But the point here is that we're getting to we can now, with just 128 CPUs on a farm, simulate that entire laminate essentially overnight and a bit anyway, I guess you could say. And that really does open up the possibilities of analysis that we wouldn't normally contemplate for a package like that. Okay. So this table just summarizes the results. I don't need to go through this in detail, but I will stress again, from a single machine to 256 CPUs to 128 CPUs, completely different run on the farm. Clarity was very robust. It produced the exact same final simulation result in terms of unknowns, delta S, and so forth, and the S parameters themselves, right? So this from our perspective, this is a sign that it's very well engineered in how it does the distribution of the problem across a farm. Okay, all right. And then there's lots of ways you can sanity check. You can obviously compare measured results to other simulators, like I showed you earlier. You can compare them to, simulated results to other simulators. You can compare them to measured results and so forth. There's a lot of other things we check for example, passivity. In this particular large simulation, no serious passivity violations. These numbers should not be much larger than 1, otherwise you have passivity problems, and they're not. And then another interesting thing I want to show is we looked at the S parameter data from those 3 different simulations: the dedicated machine, the 256 job on the farm, and the 128 CPU job on the farm. And then we compared them, all 3, one against each other, and looked for the worst case error in the S parameters. Because what you're looking for is, has Clarity gone and done something wrong in the process of distributing this problem across the farm? And you can see here the worst case for Sim 1, which is the dedicated machine, and Sim 2A, which was the 256 CPU job, was 140S, 149, 143. And I plotted those 2 curves here, and the RMS error was 4.7 e to the minus 5 for that single S parameter over the full frequency range. That's very, very small, and you can see that visually as well. So effectively, no change in the S parameter value. Sim 1 to 2B, the worst case was S 151, 153. Again, you can see an excellent result. And then for Sim 2A and 2B, that's the 128 versus 256. Once again, you see an excellent result. So, all of this combined gives us a lot of assurance that Clarity is very robust in how it handles this distribution of the simulation problem. Okay, check the time. Okay, so that brings me to my conclusions. Clarity results were shown for two different simulation examples. The first was that multi-die signal chain product, and then the second is one of our high-performance SoC on laminate products. And the results that we have seen to date, we trust. And one of the reasons we trust those is we've seen good agreement, a lot more than what I showed you in the two slides, and on other designs as well, I would add, with another commercial tool that we use and have used for a long time and trust. So to date, we have a lot of trust in the results that we're getting from Clarity. As I hope I've shown you, Clarity is very efficient at partitioning large problems into smaller pieces and using modest farm resources to simulate those smaller pieces. This is a point I want to really stress, is the robustness of Clarity. If jobs die for some reason, Clarity keeps going. This is very important if you're trying to do a job over a large number of compute farm nodes. Clarity has impressive single machine performance. That's not typically where you might use Clarity, but if you did have a single high performance machine to use Clarity on, it's, does very, very well. Okay. The GUIs are very easy to use, both for the 3D layout and 3D workbench. They're powerful, robust, and they simplify a lot of time-consuming tasks. I would also add that Clarity, I don't have it here, but Clarity has a batch mode tickle. You can use tickle TK to control Clarity, and we've been looking at that a little bit. So that's another alternative way to run Clarity simulations. And large problems that would either be slow or completely impractical to simulate, even on big, powerful machines. We've run larger problems than the one I've shown you, by the way. We've gone up to beyond 100 million unknowns, and Clarity has had no trouble whatsoever with those problems. Right. So if you're trying to solve system-level electromagnetics on single dedicated machines, it gets very, very costly. You can run into the $100,000 type of machine. And even then, you may not be able to solve the problem. And then one area not covered in this talk, but that we're looking at now, is the inclusion of IC layers. I drew some simple ideal ground planes that you saw on those die earlier, but we're now looking at actually including top-level IC metal in the simulations, which can be very important when there are IC package interactions and you're trying to model system performance from the IC all the way out to the boundaries of the system. And finally, just some acknowledgements. Some folks at Analog Devices I'd like to acknowledge for the designs that I showed you. And then at Cadence, I'd like to acknowledge Lawrence Durr, who has been superb in his support and expertise with Clarity. He's a Clarity applications engineer that's worked closely with us. And I'd just like to acknowledge the R&D team for their help debugging a few issues we have. We haven't had a lot of issues with Clarity, I'll be honest. But we haven't had some engagement with the R&D team, and including Matt Sabino and others there. So I'd like to thank them as well. And that brings me to the end of my presentation, and I would be happy to take any questions if you have them. Thank you very much.